All right, everyone get ready, because today we are going deep, deep down into the world of neutrinos.
Oh, yeah.
Those itty-bitty, almost massless particles
Yeah.
that travel for billions of years.
Billions of light years, yeah.
Across the universe, carrying secrets about
Right.
the most extreme events imaginable.
They really are fascinating.
Absolutely. And we are joined by
An expert.
an expert
That's me.
to help us unpack this recent discovery by KM3NeT.
Yay.
That's a massive underwater telescope that
Which just
detected the highest energy neutrino
ever
recorded.
It's pretty exciting stuff.
Absolutely. And as Yorgo
A schnitpad.
lays out in his essay,
Yeah.
this is really kind of shaking things up in the world of astrophysics.
It is. It's really changing the way we look at things.
Absolutely. So,
So where do we even begin?
well, I think maybe we should start with like a little bit of a refresher on neutrinos themselves for our listeners who maybe aren't as familiar. Can you give us like the Spark Notes version
Sure, yeah.
of what a neutrino is?
Okay, so neutrinos, they're these subatomic particles.
Right.
And they're incredibly tiny. They're almost massless.
Okay.
And what's really cool about them is they barely interact with matter.
Meaning that
They
can just like zip right through things.
they can travel billions of light years across the universe without really bumping into anything.
Wow. So like,
Yeah, it's
I'm
incredible.
picturing like a little tiny spaceship just like dodging asteroids
Yeah, kind of like that.
as it goes through space.
Yeah, that's a good analogy.
But in this case, the spaceship is like
It's a tiny particle,
smaller than an atom.
way smaller.
Yeah. And they're carrying these messages
Right.
from the
Like
most
detectors.
powerful events in the universe. Yeah.
So how, if they're so hard to catch,
right.
how does KM3NeT find them?
That's a great question. And it all comes down to some seriously clever engineering and physics.
Mm-hmm. So KM3NeT is actually submerged deep in the Mediterranean Sea.
What?
Yeah.
Like at the bottom?
Deep down,
Oh,
where it
so-
acts like this giant neutrino trap.
I'm already lost.
Okay, so basically imagine
Yep.
a huge grid of super sensitive light detectors
Right.
spread out over a cubic kilometer of ocean.
Cubic kilometer.
Yeah, it's enormous.
Okay.
And they're all waiting to catch this really faint flash of light called Cherenkov radiation. Cherenkov radiation.
Okay. I've heard of that.
Which is produced when a neutrino very rarely bumps into a water molecule. And by detecting these flashes,
Okay.
scientists can actually trace the path of the neutrino back to its source.
Wow.
It's like a cosmic GPS.
That's incredible.
It is pretty amazing.
So back to our record-breaking neutrino.
Right, the big one.
Where could something that powerful even come from?
That's the million-dollar question, isn't it?
It is.
I mean, we know it came from outside our galaxy.
Outside our galaxy.
But the exact source,
Yeah.
it's still a mystery.
So we're talking like,
We're talking some of the most powerful events in the universe.
okay.
Things like active galactic nuclei or AGNs.
IGNs.
Yeah, these are basically supermassive black holes
Oh.
at the centers of galaxies.
Yeah.
And they have these swirling disks of matter falling into them.
And like
Yeah.
shooting stuff out the other side.
Exactly. As this matter gets pulled in, it gets superheated.
Oh, wow.
And blasts out these jets of particles.
It's like a cosmic fire hose.
It's a pretty good analogy.
You're like a
Yeah.
really powerful
Yeah.
space
I mean,
engine.
like a giant cosmic engine churning out these high energy particles.
But how do we know
Yeah.
if it's the source of our neutrino?
Well, that's just it. We don't know for sure.
Okay.
It's one possibility, but there are others too.
Like what else could be?
Well, we have supernovae, for example.
Supernovae.
Yeah. You know, massive stars that explode at the end of their lives,
Okay.
releasing enormous amounts of energy.
Yeah, I've heard of those.
They're pretty spectacular.
And they're pretty powerful.
Incredibly powerful.
So they could,
Yeah, they could definitely produce neutrinos.
But-
But whether they could produce one this energetic is another question.
and is there anything else?
Well, there's one more suspect we need to consider.
Okay, lay it on me.
Gamma ray bursts, or GRBs.
GRBs.
Yeah, what are those?
Think of them as the universe's biggest fireworks show.
Fireworks.
Yeah, they're even more intense than supernovae.
Okay, so we're talking like,
We're talking about the most powerful explosions in the universe.
so like a cosmic laser show.
Yeah, that's a good way to put it.
Okay.
And these GRBs happen when a massive star collapses into a black hole or when two neutron stars collide.
And so like,
Yeah.
how much energy are we talking here?
We're talking about events that can release more energy in a few seconds than our sun will emit in its entire lifetime.
That's insane.
It's mind-boggling, isn't it?
So how do we even begin to figure out which of these cosmic suspects is the culprit?
Yeah. It seems like a really tough case to crack.
It is. It's a real cosmic mystery.
Yeah, it really does.
It does. It's like a giant cosmic puzzle.
And how do we even start to narrow it down?
Well, we need more clues, right?
We
need more information. And that's where KM3NeT's collaboration with other observatories comes in.
Right. It's not working alone down there in the Mediterranean.
Not at all. It's part of this global network of observatories.
Okay.
Each with its own unique way of looking at the universe.
So we're talking like space telescopes, ground-based observatories.
Yeah, we're talking telescopes that detect light, radio waves, gamma rays, even gravitational waves.
So like,
yeah,
we're combining all this data.
Exactly. By combining data from all these different sources, we can start to build a more complete picture of the event that produced our high-energy neutrino.
So it's like
having multiple witnesses to a crime.
Okay.
Each providing a different piece of the puzzle.
So we might find, say, a gamma ray burst detected by a space telescope. That lines up perfectly with the direction of our neutrino.
Exactly. And by comparing the timing of these different signals, we can even start to narrow down the distance to the source.
So we can kind of like triangulate?
Yeah, it's a bit like triangulation.
Okay.
This is what we call multi-messenger astronomy.
Multi-messenger astronomy.
Yeah, and it's really revolutionizing the way we study the universe.
That's pretty incredible to think about.
It's really exciting.
It is. What about KM3NeT itself?
Right.
What makes this thing so special?
Well, for one thing, it's really pushing the boundaries of technology.
Sure.
One of the really key innovations in KM3NeT is the use of these multi-PMT optical modules.
Multi-PMT, okay.
Yeah. So instead of relying on a single large photomultiplier tube to detect light, each module in KM3NeT has 31 smaller PMTs.
31?
31, yeah.
So it's like having 31 eyes.
It's a good analogy.
Okay.
Imagine you're trying to see a faint star in the night sky.
Yeah.
The bigger your telescope, the more light you can gather, and the easier it is to see that star.
Right.
But with neutrinos, we're dealing with incredibly faint signals.
Oh.
So instead of one big eye, KM3NeT has 31 smaller, more sensitive eyes.
Okay.
In each module, making it much better at detecting those faint flashes of light from neutrino interactions.
Okay, so it's more sensitive.
Way more sensitive.
Okay.
And that's not all.
Okay.
KM3NeT also uses some really sophisticated data analysis, including machine learning algorithms to sift through this massive amount of data.
Right, because if it has 31 times the
it's generating a lot of data.
Yeah.
Exactly. And this helps scientists identify those really rare neutrino interactions from a sea of background noise.
So AI is helping us.
Absolutely. AI is playing a huge role in this.
Unlock the secrets of the universe.
It's pretty amazing.
That's mind-boggling.
Yeah, and that's just the beginning.
Okay.
KM3NeT is still expanding.
Okay.
And as it grows, its capabilities are only going to increase.
So like imagine a future with like even more sensitive detectors.
Absolutely.
Covering an even larger volume of the ocean.
Yeah, imagine what we'll be able to see then.
So like catching even more of these neutrinos and like building a more...
Exactly, a more detailed picture of the neutrino sky.
Okay.
We might be able to pinpoint the locations of those cosmic accelerators with incredible accuracy.
Wow.
Identify new types of neutrino sources.
Okay.
Maybe even unlock the mysteries of dark matter and dark energy.
Dark matter.
Yeah. Who knows what else KM3NeT might reveal.
That's incredible.
Pretty exciting stuff.
It really is. It gives you a sense of awe for like how much is out there that we don't know.
Exactly.
But before we get too carried away thinking about like the vastness of space, let's bring it back down to Earth for a second.
Right.
What does all this mean for our listeners?
Right.
Why should they care about these?
Yeah, good question.
Tiny part.
Yeah, why should anyone care about these things zipping through us all the time?
Yeah, it's easy to get lost in all that.
It is, yeah. You start thinking about the scale of the universe and you realize how small we really are.
Yeah, and how much we don't know.
Exactly, but I think that's also what makes it so fascinating.
It is.
It's this sense of wonder and the realization that there's always more to learn.
So maybe these neutrinos, they can teach us something about our place in the cosmos.
I think they can. I think this discovery, this quest to understand neutrinos and the universe, it embodies this very human desire to explore the unknown.
Right, like it's not even necessarily about the answers.
No, it's about the journey.
It's about
pushing the boundaries of what we know, like, Jürgen Schneeplatt has done with his work.
Right.
I mean, who knows what other secrets are out there just waiting to be uncovered?
Yeah, like maybe there are new types of neutrinos that we haven't even imagined yet.
Exactly. Or maybe neutrinos hold the key to understanding dark matter and dark energy. Yeah, these mysterious forces that shape the evolution of the universe.
Right.
It's mind-boggling when you really think about it.
It is.
And KM3NeT, it's going to play a leading role in all of this.
Yeah, as it keeps expanding.
Right, with its continued development and with all these collaborations, it's really poised to make some groundbreaking discoveries.
So as we're wrapping up this deep dive,
Yeah.
what's the one thing you want our listeners to take away from all of this?
That's a good question. I think the most important thing is to remember that the universe is a vast and mysterious place.
Okay.
And we humans, with our curiosity and our ingenuity, we're constantly striving to understand it better.
And every new discovery, every piece of the puzzle we uncover, it brings us one step closer
to unlocking the secrets of the cosmos.
Exactly.
So next time you're feeling small or insignificant, just remember those tiny neutrinos.
Okay.
Zipping across the universe carrying secrets billions of years old.
Yeah.
It's a reminder that we're all connected to something much larger than ourselves. And who knows, maybe one of our listeners inspired by this very episode will be the one to make the next groundbreaking discovery.
Yeah, so to all our listeners out there, keep looking up, keep asking questions.
Yeah.
And never stop exploring the wonders of the universe.
Well said.
That's it for this deep dive, folks.
Until next time.
We'll catch you next time.